So in previous lessons, we've looked at how matrices can be used to describe transformations of the plane. We're now going to look at another use for matrices, and that is to solve systems of equations. So we're going to look at solving simultaneous linear equations using matrices. So we're going to consider how a matrix could be used to solve the simultaneous equations given below. The first thing we need to do is rewrite this problem in matrix form. So this can be written as A, which is going to be a matrix, a square 2 by 2 matrix, times xy equals, and then B is going to be a vector. So for this system of equations, it can be written as 2, 3 minus 4, 1 times xy equals 16, 3. Let's just look at why that is. So the right-hand side will expand 2, 3 minus 4, 1 times xy. If you were to multiply that together, you'd end up with 2 times x and 3 times y, so 2x plus 3y. That's going to be the top of the vector. And then we're going to have minus 4 times x and 1 times y, so minus 4x plus y. So that vector there, you will notice that that is the left-hand sides of the original simultaneous equations. Similarly, the right-hand side is just the two solutions, 16 and 3. So writing that problem in matrix form means that we can now find the inverse of the matrix. So the inverse of matrix A can be found using the matrix inverse formula. That is A inverse there. So we can now multiply each side of the equation by A inverse. So beginning with AXY equals 16, 3. We're going to multiply both sides by A inverse. So we're going to get A inverse AXY equals A inverse 16, 3. Now that left-hand side is going to simplify down. A inverse times A is the same as the identity matrix. That's what the definition is of an inverse. So A inverse A times XY is the same as just the identity matrix times xy. And because we know the identity matrix doesn't change a vector at all, we know that is just the same as xy. So the left-hand side is going to simplify right down to just xy. The right-hand side is going to be the inverse matrix A inverse multiplied by 16, 3. So we can just multiply that out together. It's easier if you multiply the matrix with the whole numbers in first by the vector and then divide by 14 at the end. So the matrix multiplied by the vector becomes 770. When we divide by the 14, we end up with 0.55. So that is telling us that the solution to the simultaneous equations is x equals 0.5, y equals 5. You can go back and check that in the original equations to check that that solution holds. So in this question, we're going to look at how matrices can sometimes satisfy certain equations. Now we're going to revisit these later on in second year when we look at characteristic equations. But for now, we're just going to start with the matrix A, which is defined as 3, 1, 5, minus 1. And in part A, we're just going to show that A satisfies that equation. So that A squared minus 2A minus 8 times the identity gives us, now that's not just the number 0, that is the 0 matrix. So substitution is going to help us here. So A squared is just the matrix A times itself. It's given us 14, 2, 10, 6. So when we calculate A squared minus 2 times A minus 8 times the identity, which is 1, 0, 0, 1, we end up with the 0 matrix. So we have shown that matrix A satisfies that equation there. For part B, I'm now going to let B be the matrix A inverse, and we're going to use that to show that B can be written as a scalar multiple of A plus another multiple of the identity. Now to start with, it's not obvious what's going to happen here. So we're going to start with the original equation. We're going to go from there. So for part B, we've been told that matrix B is defined as A inverse. And we're asked to show from that that B can be written as a scalar multiple of A plus another scalar multiple of the identity matrix. Now it's not entirely obvious at this point how this is going to work. So we're going to start with what we've been given and go from there. So we're going to start with the equation a squared minus 2a minus 8i equals 0. Now we still need to get rid of the a squared because we can see that the thing that we're looking for, the answer we're looking for, doesn't have an a squared in it. So we're going to use the inverse matrix to help with that. Now we can multiply every term by a inverse, and it doesn't matter whether you multiply every term on the left or every term on the right, as long as you are consistent. So in this case, we're going to multiply every term on the right by a inverse. So we get a squared a inverse minus 2a inverse minus 8i a inverse equals 0, the 0 matrix times a inverse. Now some of these are going to cancel. So for example, the first term is actually a times a inverse. And because we know that a times a inverse is just the identity matrix, and the identity matrix doesn't change other matrices, we can see the first term is just going to be a. So similarly, for the second one, we can see that a times a inverse is just going to become I. The third term, we can see that I times a inverse is just going to be a inverse. And because the question defined a inverse as being matrix B, we've replaced the a inverse with B in this part. And then the right hand side, we've got 0 times a inverse. We know that the 0 matrix times anything is just the 0 matrix, so that stays the same. We're now going to rearrange that because we're now being asked to find B. So if we start by adding 8b onto the other side, we can then divide everything by the scalar b, leaving us with an eighth a minus a quarter of I equals b. So we've actually found the values of alpha and beta from the question. We can see that alpha is an eighth and beta is minus a quarter. Now complete exercise 7e on page 158.